Let's now have a look at some common univariate continuous distributions. Recall that a random variable x is said to be continuous if it has a probability density function, i.e. if and only if there is a function f sub x such that the probability that x lies between a and b is just the integral from a to b of the density function. The simplest distribution is the uniform distribution. The uniform distribution on the interval from a to b models the choosing of a number randomly from that interval, with all the choices being equally likely. In that case, the probability that the chosen number lies in some subinterval of ab is proportional to the length of that subinterval. Hence, if x has the uniform distribution on the interval ab, then the probability density function and the cumulative distribution function are given by the following. The density function is constant with value 1 over b minus a on the interval from a to b, and it is 0 outside that interval. The cumulative distribution function, on the other hand, is 0 below a, is a straight line with slope 1 over b minus a from a to b, and takes the value 1 if x is greater than b. The standard uniform distribution is the uniform distribution on the unit interval from 0 to 1, and this is implemented as the RAND function in most scientific programming languages. We have already informally introduced the normal distribution. This is the most important continuous distribution because of the so-called central limit theorem, which we will cover later. The central limit theorem essentially says that a sum of a large number of independent, identically distributed random variables will be approximately normally distributed. The normal distribution with parameters mu and sigma squared, or with mean mu and variance sigma squared, has the following probability density function. Its graph is the familiar bell-shaped curve. This will have its maximum at mu. In this case, mu is equal to 1. And its width will be determined by sigma. And we've already seen the S-shaped curve that is its cumulative distribution function. We shall see that if x is normally distributed with parameters mu and sigma squared, then its expectation will be mu and its variance will be sigma squared. Expectation and variance will be introduced soon. The standard normal distribution is the normal distribution with parameters mu is equal to 0 and sigma is equal to 1. Another important distribution is the exponential distribution. This is often used to model lifetimes or survival times. If capital T has the exponential lambda distribution, where lambda is a strictly positive real number, then the probability that capital T is greater than t is e to the minus lambda t. For example, capital T might be the default time of a corporation. If capital T is strictly greater than t, then the corporation has not yet defaulted by time t. In other words, it has survived at least until time little t. The CDF of capital T is therefore, by definition, the probability that capital T is less than or equal to t, and that will be 1 minus the probability that capital T is strictly greater than t. In other words, 1 minus e to the minus lambda t. And this is for all t greater or equal to 0. The cumulative distribution function will be 0 for t less than 0. The probability density function is simply the derivative of the cumulative distribution function. Again, for t greater or equal to 0, the density function is 0 for t less than 0. Now observe the following interesting property of an exponentially distributed random variable. The probability that capital T is strictly greater than t plus h, given that we know that it is strictly greater than t. In other words, the probability that, say, a corporation will survive. In other words, for example, the probability that the corporation will survive at least until time t plus h, given that we know that it has already survived until time t, is by definition of conditional probability given as follows. Now this set here, the event that the corporation survives at least until time t plus h, is a subset of the event that it survives at least until time t. So this intersection is simply the smaller set here. At the top we have e to the minus lambda t plus h. At the bottom we have e to the minus lambda t. So there is some cancellation and we obtain e to the minus lambda h. And this is precisely the probability that t is strictly greater than h. So the probability that the corporation survives at least another h units, given that we know it has survived until time t, is the same as the probability that the corporation survives h units. The exponential distribution is therefore said to be memoryless. If t is an exponentially distributed survival time, then the fact that t has already survived little t years has no influence on the probability that it will survive another h years. It does not remember that it has already survived for t years. This is very different to human lifetimes. Given that you've survived 22 years, the probability of surviving another 50 years is quite large. But given that you have already survived 55 years, the probability of surviving another 50 years is minuscule. Your body knows or remembers how old it is. The exponential and Poisson distributions are related. Suppose that t1, t2, etc. is a sequence of independent, exponentially distributed variables with parameter lambda. Think of the Tn as inter-arrival times, i.e. the time between events. Let Sn be the sum of the first n many Ti's. Then Sn is the random time of arrival of the nth event. In other words, the nth event arrives at time Sn. Let Nt be the number of events that occur by time t. We can then show that Nt is Poisson lambda t. In other words, that the probability that Nt is equal to n is given by this expression here. Here is a little bit of intuition for this. Suppose that events arrive independently at a rate of lambda per unit time. We then know that this is modeled by the Poisson distribution with parameter lambda. Suppose also that the previous event arrived at time t0. Let capital T denote the waiting time till the next event. Thus the probability that capital T is strictly greater than little t is the probability that there are no events between t0 and t0 plus t. Since the rate of arrival is lambda per unit time, we expect lambda t many events between time t0 and t0 plus t. Let n be the number of events between t0 and t0 plus t. Then we know that n is Poisson distributed with parameter lambda times t. Now the probability that capital T is strictly greater than t is the probability that the next event arrives after time t, in other words the probability that there are no events before time t. And because n is Poisson distributed, that is given by this expression over here, which is just e to the minus lambda t. In other words, the probability that capital T is strictly greater than t is equal to e to the minus lambda t, and this means that t has the exponential distribution with parameter lambda. So if events arrive uniformly at a rate of lambda, in other words they are modeled by a Poisson distribution, then the arrival time of the next event is exponentially distributed with parameter lambda. The final distribution that we want to introduce here is the so-called gamma distribution, and to do that we need to introduce first the gamma function. This is a function which occurs frequently in statistics and in fact in scientific computing in general, and it's defined as follows. Gamma of x is equal to the integral from 0 to infinity of u to the x minus 1 e to the minus u du. Here u is the variable of integration and x is the variable that we put into the gamma function. It has the following basic properties, which we leave as an exercise. Gamma of 1 is equal to 1 and gamma of x plus 1 is equal to x times gamma x. This is easy to prove using simple techniques of integration, but as a result, it follows that if n is a positive integer, then gamma n is equal to n minus 1 factorial. It's also the case that gamma of a half is equal to the square root of pi. Here is the graph of the gamma function. As you can see, it's undefined and has asymptotes at every integer less than or equal to 0. The gamma distribution is then a distribution derived from the gamma function. It has the following PDF. The gamma distribution has two parameters. alpha and lambda. Alpha here is the so-called shape parameter, and lambda is the rate parameter. Now, many textbooks and software packages will instead have a so-called scale parameter. And the scale parameter is simply the inverse of the rate parameter. Here are some graphs of the PDFs of the gamma distribution for various values of alpha and lambda. Note that the gamma 1 lambda distribution, in other words with alpha is equal to 1 and lambda is equal to lambda, has the following PDF, and that this reduces simply to lambda times e to the minus lambda x. Now this is precisely the PDF of the exponential distribution with rate parameter lambda. In other words, the gamma 1 lambda distribution is precisely the exponential lambda distribution. Later, we shall introduce a number of other distributions, including the t-distribution and the chi-squared distribution, which are important for the statistics of the sample mean and variance of normally distributed random samples. We shall see that the chi-squared distributions are again just special cases of the gamma distribution.